So hello friends, we'll be discussing about truss structures in this class. So what is a truss? Truss, in truss structure, truss is a very simple truss. In truss structure, all the members are joined by pins, frictionless pins, and the members are assumed to be weightless, or their weights are negligibly small compared to the applied forces, and on each element the forces are only at the nodal points. There are no force internal to the element. So in that case, each member can be assumed to be a two force, or can be considered to be a two force member. And you know from your mechanics class, in a two force member, the members are along. Suppose you take this element, so the member will be, the forces will be along the line joining the two nodes, either tensile if it is outwards, or compressive if it is inwards. So for this element, it will be either inwards or outwards. So if it is outwards, it is tensile, and if it is inwards, it is compressive. So how can we analyze these truss structures using our knowledge, our previous knowledge of spring elements? So that is the topic of discussion in this class. So we have seen this spring element. So this is the axial direction of the spring element. This is the axial direction of the spring element, and we know what is the stiffness matrix of the spring. But here what we do, here in addition to these 2 degrees of freedom, we add another 2 degrees of freedom, which is perpendicular to the axis of the spring. So this is the first degree of freedom, this is the second degree of freedom, this is the third degree of freedom, and this is the fourth degree of freedom. So what will be the stiffness matrix? The stiffness matrix will be same, but we are actually inflating the degrees of freedom, and we are adding 2 perpendicular degrees of freedom. This U2L and U4L are displacements along those extra degrees of freedom. Now why are we taking this extra 2 degrees of freedom? That we'll discuss a little later. Now see, this, due to this U2L, in the spring there will be resistive force. There will be resistive force, tensile or compressive, if the displacements are along the axis of the spring. If there is a displacement perpendicular to the axis of the spring, that means due to this U2L or U4L, there cannot be any F1, because F1 depends only on U1L and U3L. And whatever displacement you give in the axial direction or in the transverse direction, F2L will always be 0. So here we put 0, here we put 0, and the axial degrees freedom has gone here at 1 and 3. So previously that K and minus K are there for the first and third degrees of freedom, and here also they are for first and third degrees of freedom. So this second column, second row, and fourth column or fourth row are added, and the spring stiffness matrix is inflated. So this stiffness of the spring we called Ke, and the element stiffness matrix in the local coordinate system. So just let us write it as Ke. Let's make it green. Ke L. So this is the spring stiffness in the local coordinate system. Local coordinate system means the x is along the length of the spring and y is perpendicular to the length of the spring. So here we have shown that F1L is this. So whatever be the value of u2l, there cannot be any f1l. So here we have put 0, and whatever be the value of u4l, there cannot be any f1l. So here we have put 0. And if you think of f2l, which is here, f2l will be 0 whatever be the value of u1l, u2l, u3l or u4l. So for f2l all the stiffness coefficients would be zeros. So I think now you understand this inflated stiffness matrix. So we add 2 extra degrees of freedom, and due to this extra degrees of freedom, the spring stiffness matrix has become a 4 by 4 matrix instead of a 2 by 2 matrix in the previous case. So, and you know the basics of coordinate transformation. Suppose this is the local degree of freedom, and this is the local coordinate system. This is a local coordinate system, and this is the global coordinate system. So what is the local coordinate system and global coordinate system? See here, if you take this simple truss, so for this element, this is the local direction. For this element, this is the local direction, and for this element, this is the local direction. So how can we appropriately add the stiffnesses from this and this? For that we have to consider the stiffnesses, or we have to transform these stiffnesses in this local coordinate system to a common coordinate system, say this one. So this we call the global coordinate system. So here say this xg and yg are the global coordinate system, and xl and yl are the local coordinate system. Now an unit vector along this will be having magnitude 1. So we can write 1 along il is equal to cos theta along ig and sin theta along jg. So this is what we are writing. And 1 along jl equal to minus sin theta along ig and plus cos theta and plus cos theta along jg. So this is the relation between il jl and ig jg. So we can easily put it in a vector. So this is the vector relation. So this is lambda, which we call the transformation matrix, and lambda is an orthogonal matrix. That means the determinant of this is 1 and the transpose is inverse. So this lambda is an orthogonal matrix whose inverse is the transpose. So the transpose means the row has become column. So ig jg is this lambda inverse this, and lambda inverse is just interchange of row and columns. Now any vector if you take, say a, so and that a vector can be expressed either in global coordinate system or in the local coordinate system. So a you can express either like this or like this. So a can be expressed as this in vector notation. This is this into this, and or this. So this is a vector in matrix notation, rather it is this into this. But we know that ig jg equal to cos theta minus sin theta cos theta il jl. So from here we get x. Now if you multiply this and this, if you multiply, and you know this is lambda transpose, so this is, so axl ayl is this into this, because iljl is there at the end of the both left hand side and right hand side. So axl ayl is axg ayg into lambda transpose. Or if you take transpose of this, then axl ayl column vector is equal to lambda into this. So so these are the components of the vector A. That means the u1L and u2L. So what is u1L and u2L? u1L and u2L are the components of the displacement vector at the first node along in the local coordinate system. And in the global coordinate system they are u1g and u2g. So that means from here, if any vector transforms according to this rule, then the displacement at node 1, that's for the first node, will also get transformed according to this relation, and the displacement at node 2 will also get transformed along this according to this relation. Now if we just put this vector under this vector, so here I have made one mistake. So this should be u1L. So let us do u1L, u2L, u3L, u4L, and this should be u1G, u2G, u3G, and u4G. So this is the relation lambda, and u1L, u2L are in no way related with u1L and u2L are in no way related to this vector. So this is a 2 by 2 null matrix. Again u3, ul is in no way related to u1g to u2g because these are different vectors. So here a null matrix and here lambda. So this whole matrix we call the transformation matrix, and transformation matrix is also an orthogonal matrix and its inverse is the transpose. So here is the relation which we are getting. So this is lambda, 0, 0, and let us call this as the local u, and this we call the global u. Similarly, the forces, the local forces on the element and the global forces on the element also related in the using the same relation. This we call FL and this we call FG. So this is UL, this is UG, this is FL, and this is FG, and they are related by this transformation matrix. So this is UL and this is FL. So I think let us go to the diagram once more. So this is FL, F1L, this is F2L, and this is F1G, and this is F2G. Now see, we know that FL is KEL into UL. Now FL means T to FG, and KEL and UL means T into UG. So if you want to find out FG, then you have to pre-multiply it with T inverse, and pre-multiply this also with T inverse. So we get this, and we know that T inverse is nothing but T transpose. So FG is equal to T transpose KEL T UG. That means this is actually the stiffness matrix in global coordinate system, because FG and UG are related by this KE, where K is this T transpose KEL T. So this is how the stiffness matrix. So if you know the transformation matrix, then you can transform the stiffness matrix in local coordinate system to the stiffness matrix to the global coordinate system. That means Now if you do this multiplication, because you know what is there in T, you know that in T these are the terms. So if you actually multiply, you perform the matrix multiplication, then you get K as K into cos squared cosine minus cos square minus cosine, and like this. And this matrix is a symmetric matrix. So all stiffness matrices are symmetric. So now you can replace, if you have a bar element in place of a spring element, then this K has to be replaced by AE by L, where A is the cross-sectional area, E is the modulus of elasticity, and L is the length of the element. So how to get cos theta and sin theta? That means how to get this C and S, and we are using C for cos theta and S for sin theta. So just you know the coordinates of this point and coordinates of this point. So first find out the length of this, then you find out the cos. Cos is this x, that means if you take this is x of n2 minus x of n1 divided by L, give you the cos, and y of n2 minus y of n1 will give you, divided by L will give you the sine. So you need not find out theta, and also do not try to find out theta also. Just use the cos and sine, which you can easily get by subtracting the coordinates and dividing it by the length. So because if you want to find out theta and you use the inverse functions like cos inverse, sine inverse, tan inverse, then trigonometrical inverse always gives the acute angle. So when the angle is not acute, it's obtuse, then it's difficult, because it will always give you the acute angle, and you can invite mistakes. You can make mistakes. So here you see, so for this, what is theta? Theta, if this is 1, this is the local coordinate 1, and this is the local coordinate 2. So 1 to 2, and this is the angle it makes with the x-axis, global x-axis. So theta is from global x-axis to this. Now if this is 1 and this is 2, then the vector is in this direction. So from x, this is the angle, okay, in anti-clockwise direction. If this is 1 and this is 2, then here to here. And if this is 1 and this is 2, so the vector is along this 1 to 2 vector. So this is this. So in this way, the angles are angles. If you want to find angles, you have to find angles taking this into account. Anyway, you need not find out the angles. So here is a simple example where this is a hinge, this is a hinge, and this is not a hinge. So just let me make the correction. This is not a hinge. This is not a hinge. This is a pin. So this is a pin. So let me write. This is the pin. Okay. So this is a pin. So all these are pin joints. So there is no force on the element. Only the forces are at the nodes. The forces are at the nodes. There are no internal force internal to the element. Not internal to the element. Force inside the element rather. No force inside the element. There is no force inside the element. Only forces. There are forces only at the nodes. So, and all the data are given. This E is called the material property data, because this is a steel structure. The E is taken as Young's modulus or modulus of elasticity of steel. A is the cross section area for this. So this it is 200 mm square, and for this it is 400 mm square. So, and the coordinates in meters are also given. These are the coordinates in meters. So this has got 6 degrees of freedom. At node 1, 2 degrees of freedom, node 2, 2 degrees of freedom, and node 3, 6 degrees of freedom. So see, In spring element there is only a single degree of freedom along the axial direction, but in truss element there are 2 degrees of freedom. Because, why is it so? Because, say from the first figure, so this will have this will resist forces in this direction, but this will resist forces in this direction. So we must introduce this coordinate, the x coordinate, and also the y coordinate. So there will be degree of freedom along x and degree of freedom along y. That's why we have inflated and introduce the other degree of freedom. Okay, so we were here. So while implementing this in computer, you have to use 4 different charts. So what are those charts? One is simply the coordinate, node coordinate chart. Not node chart, is node coordinate chart. So here each node is having, these are the coordinates they are having. So the first node is this one, so it's having a coordinate of 0, 1. That means x is here and y is, this is say y and x, yg, and this is xg, which I have forgotten to write. So this is xg and this is yg. So if this is so, this is not clear, this is g and this is xg. So these are the coordinates of the nodes. So this is the node coordinate chart, and here is node coordinate chart, not node chart. I will make a correction and give you the PDF file. So this is element node connectivity chart. That means element 1. So what are the nodes connected? 1 and 2. And for element 2, what are the nodes connected? 2 and 3. And this is the property index. So this is, so for this the property may be different from this. So the property index for this is different from this, and indeed it is different here. So these two are having different properties. So because the cross sectional area are different, so let us put 1 and 2. Now element DOF connectivity chart. What are the degrees of freedom? Here the degrees of freedom 1 and 2, then 3 and 4, then 5 and 6. So there are 6 degrees of freedom, and the first element is having 1, 2, 3, 4. The first element is having the degrees of freedom 1, 2, 3, 4, and the second element is having degrees of freedom 3, 4, 5, 6. And the property chart, that means this index what you are giving, this is the index which indicates the property. So one index has got, and element 1 is assigned the index 1, element 2 is assigned the index 2. There can be one element 3 which can be assigned the index 1, and element 4 which can be assigned again the index 1, element 5 which can be assigned the index 2, likewise goes. And what is index 1? Index 1 is having an area of this and modulus of elasticity of this. Index 2 has got an area of this and Young's modulus of elasticity of this. Now this is, you remember, the global stiffness matrix. So for element 1, the first node is 1 and the second node is 2. So the length is 1 and cos is, this is xn2 minus xn1, that is 1 by 1, so it's 1, and sine y, though both the y's of node 1 and node 2 are same, so sine is 0. Now if you just use the formula, then it is A by L. A is 2 into the minus 4, E is this, so 2 to the 4 into 10 to the power 7, so L is 1, so 4 into 10 to the power 7, so 10 to the power 7 we have taken as common, and 4 minus 4 minus 4, 4. And similarly, if you consider element 2, so length is 1. Since it is on the vertical line, the x's are same. 0, s is minus 1 because yn2 is below yn1 and we are taking y in the upward direction. So again, if you put the values, it should be 8 into 10 to the power 7. So we have taken 10 to the power 7 common and like this. Okay. Now see in the system degree of freedom. In the system degree of freedom, here 1, 2, 3 and 4, and this we are getting from this LDOFS. So LDOFS is saying that local 1 has gone to global 1 DOF, local 1 has gone to global 2 DOF, and local 3 has gone to not global system. So local 1 has gone to system. Because element number 1, local 1 has gone to system 1, local 2 has gone to system DOF 2, local 3 has gone to system DOF 3, and local 4 has gone to system DOF 4. And for the element 2, the local 1 has gone to 3, the local 2 has gone to 4, the local 3 has gone to 5, and local 4 has gone to 6. So here 1, this blue one is the local number, and this pink one is the system number. So this is for first element 1, 2, 3, 4. But for the second element, it's different. So 1 has gone to 3, 2 has gone to 4, 3 has gone to 5, and 4 has gone to 6. Similarly here also 1 has gone to 3, 2 has gone to 4, 3 has gone to 5, and 4 has gone to 6. So now you assemble and you first take a 6 by 6 matrix and put the stiffnesses in appropriate positions, and where there is an overlap you just add. So we have got this as our system stiffness matrix, and our force vector we have not written, and force vector will be so our force vector will be, where it's gone, example starts from here. Force vector will be here reaction 1, reaction 2. Reaction is acting on this element, reaction 1 and reaction 2. Here 500, 1000, and here again reaction 5 and reaction 6. Okay, yeah. So here I have written, but here I have missed it out. So it would be, the F would be first one reaction 1, second, for second row it is reaction 2, for third row it is 5000, for 500, this for the fourth it should be 1000, for this it is reaction 5, and for this it is reaction 6. And if you solve, what we have done, we have put large diagonal elements in the at the known degrees of freedom, and we got this as our displacement. So for element 1 we have to take first 4. For element 1 we have taken the first 4. So UG1 is this, and for element 2 these are the displacements. Now you just multiply, you just use this relation F1g equal to, you know what is K1g, and you just multiply it with UG1 and you get this, and here you get this. So that here you are getting this means minus 500 in this direction, 0 in this direction, 500 in this direction, and 0 in this direction. And for element 2 it is 0 in this direction, 1000 in this upward direction, 0 here, and minus 1000 here. So check that each element is under equilibrium, and if you just combine them, so minus 500 comes, so here 1000 from this and 500 from this, and from here 0 and minus 1000 of this. So the total structure is also in equilibrium. Okay, so yeah, here I have shown the these are the reactions and these are the reactions. So while this is whatever we have done is uh, the procedure is exactly what we do in computers, but while doing it in our exams or manually, what you do, you use row column deletion. So since u1, u2, u5 and u6 are specified, you delete first row, second row, fifth row and sixth row, and also first column, second column, fifth column and sixth column. So you are left with only this much, and here this much, and here this much. So this is your 2 by 2 equation, also decoupled 2 by 2 equation, and you solve for u3 and u4. So in the next video we will see this can be uh, how this can be analyzed by writing a computer program in Octave. So thank you. So we start with our previous program on spring elements, where you remember there are two springs, and this is the stiffness of the first spring and this is the stiffness of the second spring. This is the system stiffness matrix. This is the element DOF connectivity for the first spring, and this is the element DOF connectivity for the second spring. And there were two elements, so there was a loop on elements, and this is the assembly process. In the element, first we access the first stiffness, that is the stiffness of the first element. Then this is the local stiffness matrix, and here in the assembly part we assemble the local stiffness matrix in the system stiffness matrix. So here what we will do is, here we will just open a new script file, okay, and from here we will just keep on copying lines, because all finite element programs, they follow a pattern, and I want to show you that pattern. But spring element is the simplest element and the truss element is a little more complicated, so there will be some differences. So what are the differences, that I will also explain. So first, this program will start with CLC and clear screen and clear all workspace variables as before. Then see here, this was the example problem, and we are attempting to solve this. So first these four charts have to be given to the program as input data. Okay, so so let us first supply these two charts to the program. So xc is equal to x0 y1, then x1 y1, and then x1 and y0. So this is xc, and now this is the node coordinate chart. Then the element node connectivity chart with the property index. So let us call it L nodes. So L nodes is, so these see here, it is a 3-row vector, and the first row contains the coordinates of the first node, the second row contains the coordinate of the second node, and the third row contains the coordinate of the third node. And here this is 1 1 2 1, and here 2, 2, 3 and 2. So what are these? So here this L nodes is actually first element number. So this is the element number. This is the element number. Then the first node of that element, the number of the first node of that element, and the second node of the element 1, 2. So element number 1, and the nodes are 1, 2. And what is the next data? That is the property index. So the property index for the first element is 1, and here element number 2, first node is 2, second node is 3, and this is the property index of the second element. Okay. Here we are not giving the node numbers, but if you wish you can give, but the problem is these are of real types, the coordinates are of real types and the number is of integer type. So there will be a mixture of data types and the node number will also be taken as a real number. So we have avoided it. And the second and the third one is element DOF connectivity number, which we called element DOFs. So first element has got, so did we give the DOF number here? Here we didn't give the element number, only the DOF numbers we have supplied. See, it's not 1, 1, 2, it is just 1, 2. That means the DOFs of element 1 is 1 and 2, and 2 is 2 of 3, but the element number separately we have not given. So here also we are not giving the element number. So 1, 2, 3, 4, and then 3, 4, 5, 6. So this corresponds to this figure. 1, 2, 3, 4 for element 1. So first row means element 1. 3, 4, 5, 6. So the second row means element 2. Now we have to give the property table against the property index. So property index 1, this area, this modulus elasticity. So what we can do is, again we can omit the property index number. So prop is equal to 2e minus 4, 2e11, and here 4e minus 4, 2e11. That means this is the first row. First row corresponds to the property index 1 and the second row corresponds to the property index 2. So property index 1 will be used by this and property index 2 will be by this. Had there been a, say, third element, it would have been something like this. Say 1, 2, 2, 3, 1. Say here 2, 3. So maybe 3, 4. Element number 3, 3, 4, and here again 1. That means the third element are having first node. Third element is having 3 as its first node, 4 as its second node, and 1 as its property index. Anyway, so remove it. So let's see. So let us save it. File. Save file as. Say here we give it a name xxx4. So save. It is saved. Now you can run. Save file and run. You can run. And in the command window, the results are given. So xc, these 3 rows are the 3 coordinates of 3 nodes. This L nodes. Here only we are giving the element numbers. And these are the 2 nodes, and this is the property index. So here the degrees of freedom for element 1, degrees of freedom for element 1, and this is the properties. So okay, so let us go to the editor again. So here, so now we have to come to this loop over element. So for L_num, its element number equal to 1 to 2. There are two elements. So element number 1 to 2 and for will automatically come. So what is the so how do we calculate the stiffness of the element? So first we have to take the first two nodes. So n1 is the first node of element 1 or element L_num, say for element n1 is L0s, it is L_num 2. Okay, n1 is, or you can simply, if you don't want to give the element number here, you can write it like this. You can remove the element number. The row number is automatically the element number. So this is element number 1. This is element 2. So this is the L_num 1, and n2 is L0s L_num 2. So n1 and n2, we don't want to show it on the command window, so we put semicolon here, and x length, the length of this is xc, it is n1 2 xc n2 1. There is x, this one is for x coordinate and n2 is for the node, minus xc minus xc n1 1, this within bracket square, this is square, plus this is the square of the difference of x coordinates of node n2 and n1. So this is the y coordinate, the difference in y coordinates. So now square root of the whole thing, sqrt, square root of the whole thing. So now cos is equal to this difference, the difference in x coordinate, copy paste by x length is the length, and sine is equal to, so this one, that is difference in y coordinates, copy paste by x, and I have already done here. So file, open x663. I have already written the this formula for element stiffness matrix. So just copy it from here, and I don't require it. Okay. So here, oh my god, where's the cursor gone? It has come. There was some problem system that I was not getting the cursor. So okay. So sorry. So this got added in the this got copied in the pasted in the wrong place. Let us cut it here. Paste it here. Delete. So, so this is the formula, but still here we have to give area. So what is area? Area. So first we have to get the property index. So property index can be got by L naughts, L num, which one? 1, 2, 3. L num, comma 3. Property index, and area is prop. Area is prop. So here 3 prop, L prop 1, and E mod is equal to prop L prop, comma 2. So let us put semicolons, otherwise everything will get printed on the command window. So now if we run this loop, then let's see what happens. So run, save file, run. So if some problem here, some syntax error. So oh, okay. So what was the error? So this got in the same line. So like this. So run, save file and run. So let's see. Okay, here another error. So here one extra bracket has come. Run. Yeah, now it ran. So command window. See. So you have checked up to this. So okay, here for cos I should put semicolon, otherwise it will get printed as it got. So here command window. So prop elements. This is our element stiffness matrix. And this is the first element stiffness matrix for element 1, and this is the element stiffness matrix for element 2. Okay, so this is a loop over element. First it is calculating the element stiffness matrix for L number 1, and it is showing it here, and then it is calculating the stiffness matrix for element number 2 and showing it here. But the assembly part has to be introduced now. So assembly is same. So this for 2, this and copy. So we put it here, paste. Okay. So now the only thing is here there are 4 degrees of freedom. For j in place of 2, it should be 4 and 4. So run. So this is the command window. Where are k undefined? Okay. So here we have to first initialize k as k equal to zeros. That is a matrix, a null matrix of size 6. 3 by 3, so zeros, 6 by 6. Now say file and run. Command window. So So see here, okay, I will just put semicolon here, and after, and here I will put, just before going on to the next element, I will put one k. That is, it is taking first element, putting it in the assembled in the system stiffness matrix K, and then going to the next element. But before going to the next element, it is just printing K. So let us see what happens. Okay, so command window. It is on here. So let us take it here. So first, this is for, okay, we have forgotten to give semicolon here. So it has come, run, save file and run. So command window. So here the element stiffness matrix for element 1, and it has put the element stiffness matrix in the system stiffness matrix. Then the second element, this is the stiffness matrix of the second element, and it has put here. So this is the assembled system stiffness matrix. Okay. So let us stop here, and in the next video we'll see the solution.